which is the iron loss calculation in the transformer core in a no-load operation state. The task is simple: to calculate the core losses in the transformer, and the no-load mode means that the secondary is open circuit. The core dimensions are 60 by 60 by 20 millimeters. Transformer operates at the frequency of 400 Hz. The core permeability is 2000. The primary winding contains 400 turns, and each turn carries the current of 20 milliamperes. The core loss coefficients are the following. The geometry model is very simple, so I will create it from the very beginning. Now let's start QuickField. And I call it transformer 1. The problem type is AC magnetics. The frequency is 400 Hz. And the LZ is 20 millimeters. Now here I should draw the geometry model. In fact, I already have the drawing, so I created in AutoCAD and saved in the Excel file, so I will import the model instead of drawing it. Here is the file, and this is the geometry model. Now I should give the name to every object in my geometry model. I select the core and give it the label core. I will select the insulation and give it the label insulation. To select multiple objects, just hold the Ctrl button pressed. This is the primary winding positive, and this is the primary winding negative, back current. This is the secondary winding positive, and this is the secondary winding negative. And to limit the calculation area at the transformer core boundary, I will set the zero magnetic flux boundary condition. Now that's all. We have the core, the insulation, primary winding, and secondary winding. Now let's check the physical properties of each object. For the insulation, I will specify the magnetic permeability of 1. I do not specify conductivity, which is 0 for the insulation, and I do not specify excitation. There is no current in the insulation. For the core, I specify the permeability, which is 2000, and in fact you may specify the nonlinear dependency, the pH curve, but in this case it is specified that permeability is constant. The core is eliminated, so the electrical conductivity is 0. There is no current in the core, and I would specify the core loss coefficients, which are core iron loss coefficients. Remember, these coefficients are part of the Bertotti expression which approximate the experimental data. Okay. For the winding, I specify the magnetic permeability of 1 and the total current, which is 20 milliamperes multiplied by the number of turns, negative. And for the positive, again, magnetic permeability of 1 and the total current 20 milliamperes multiplied by the number of turns. There is no current in the secondary winding, so I specify only the material physical properties, permeability of 1 and 0 electrical current. And as I said, we limited the calculation area, so at the external boundary I set 0 magnetic potential. Now everything is ready and we can run this simulation. Well, the last step is to build the finite element mesh, save all problem files and run the analysis. And here you can see the result, the magnetic field distribution in the core. You can adjust the field picture for example. I will show up the flux density distribution. You see that here in the corners, in the internal corners, the flux density is higher than in these places, so you can expect higher losses in these parts. Now let's take a look at the losses distribution. Again, I will adjust the field picture to show up the power losses distribution. Indeed, here are the places of the higher losses. Now let's calculate the overall losses in the core. To do so, you can use the contour tool to select the core and open the integral calculator. And here is the core loss. Bertotti expression is not the only one which is used to approximate experimental data of iron loss. In many cases, the Steinmetz equation is used, and there are other equations as well. So we implemented custom integral calculation in QuickField. Custom integral may use any user-defined expression. It is implemented using programming interface. It's advanced technique, so I will show it in all details. But first, let's take a look at the integration process in QuickField. When you ask QuickField to calculate integral over the selected area, in fact, QuickField calculates the predefined function in the mesh nodes. In every mesh node, the value is calculated. Then QuickField finds the sum, and here is the result. In a similar way, the custom integral process works. QuickField sends all the field parameters calculated in the point and read the custom function value from your program. The process is repeated for each point, and then the total integral value is calculated in QuickField. This technique could be used with any problem type and any expression, and there are a lot of parameters that could be calculated in the point. But in case of core loss calculation, we need only the flux density value. And the program code that calculate losses is very short. We used Microsoft Excel to make a programming example. Now let me show you. You can see the interface is very simple. You should follow the general steps of integral calculation. You should open QuickField and select the integration area. As I said, during the integration process, QuickField sends the values in the mesh nodes to our program. From these values, we extract only the flux density, which we put in this cell. In this cell, we calculate our custom function value using the flux density, the frequency, and these coefficients, and send this value back to QuickField. Now let me run the process and show you how it works. The progress indicates which mesh node is currently under calculation, and as I said, for each mesh node the flux density value is put in this cell. The loss are calculated using this custom function, and the result is sent back to QuickField. The process took about 1 minute because there is the between program interaction, and after 1 minute waiting you will get the total loss value. And if you compare these two values, you can see they're the same because I used this same equation and the same coefficients. The Bertotti expression is not the only one which is used to approximate experimental data of the iron loss. And for example, I will modify this script to use the Steinmetz equation. Steinmetz equation looks like k multiplied by the frequency in the power of a multiplied by the flux density in the power of c. Here is the Steinmetz equation. Now here I will type in the coefficient k, a, c. Here you should specify the values of this coefficient. I have some values for another electrotechnical steel. Now we should correct the loss calculation equation. Now it's k multiplied by the frequency in the power of A multiplied by the flux density in the power of C. Now let's run the calculation process and get to know which will be the total loss for this new material. Again, after about 1 minute waiting, the calculation is done. And here are the total losses calculated for this specific material using the Steinmetz equation. You may note that I haven't done any programming yet. I only changed the equation in this cell and the losses were calculated. I will show you the code that is implemented in the Excel file later, and now we will move to the next example.